Hello everyone. Here we are going to discuss the various types of electrical systems in Alco type diesel locomotives. Now coming to our first topic, that is E-type excitation system. We first need to understand the meaning of the term excitation control. As we know, the voltage output of a generator depends on the speed of the armature and the amount of the field excitation. The current, on the other hand, depends on the circuit connected to the generator, usually called as the load. In a diesel electric locomotive, the load consists of the traction motors with their cables and switches. These motors should have the right voltage at all times. To get the right voltage, the current in the generator field must be varied to suit the locomotive's operating condition. This is known as excitation control. The electronic excitation system is known as E-type excitation system. In this system, main generator field is excited by a DC generator called exciter. Field of exciter is fed from battery through control. Average current flowing through the generator exciter field is controlled by a power transistor called exciter field transistor working in switching mode. A magnetic amplifier called pulse width modulator controls on and off period of exciter field transistor on getting different input signals of engine speed, main generator voltage and the main generator current. Now let us discuss the functions of the E-type excitation system. A diesel engine gives maximum fuel efficiency if it is loaded in such a way so that it develops constant horsepower with each throttle setting. In a diesel electric locomotive, load consists of the traction motors and the current through them varies with the change in speed. So, to keep the main generator power constant, the output voltage must be varied accordingly. The purpose of the excitation system is to ensure that the traction alternator demand matches the capability of the diesel engine throughout its entire speed range. If adequate control of alternator demand is not provided, one of the following will occur. If the alternator demand exceeds engine ability, the engine will slow down or bog with still further loss of power. The locomotive will be unable to perform its job and may result in engine damage. If the alternator demand is less than the engine ability, the governor will reduce fuel to prevent the engine from overspeeding, but it will not be possible to utilize the full rated power of the engine, and the locomotive will not be able to pull its rated load. Hence, the excitation system must also impose electrical limits on the main generator, that is, maximum voltage and current, to avoid the possibility of damage to the insulation by high voltage or excessive current. In the locomotive, the load on the main generator at any fixed engine speed varies as locomotive track speed increases due to counter EMF generated by the rotating armature of the traction motors. Therefore, the excitation controls must keep the alternator HP demand constant over a wide range of terminal voltage. The E-type excitation system controls exciter field current and the exciter output in turn controls traction alternator output. The system provides the functions of current limit, horsepower and voltage limits of the alternator at each of the engine speeds. The alternator is a three-phase AC output is rectified to the DC by a three-phase rectifier. The alternator rectifier set output feed the traction motors. Shown here is the alternator rectifier load curve. The required performance is shown by a typical curve above for 8th notch operation. The slightly rising line from the origin of the curve from A to B is known as the IR line. This represents the voltage obtained at various alternator rectifier currents with the motors connected, but with the train at standstill. The portion of the curve denoted by line BC is the current limit for alternator rectifier. The currents in excess of the value shown by this line would produce excessive slippage while starting the train. The current and voltage combination represented by points along the line CF indicate a constant rated engine horsepower. The voltage and current to the right of this line would represent an overload on the diesel engine. If the excitation system allows overload of the engine, then controlled operation could not be obtained. The dotted line represents the characteristic by the excitation system to approximately full engine horsepower. The system tolerances are such that actual alternator rectifier demand may fall anywhere in the band shown, meaning that in some instances demand may slightly exceed normal engine ability. When this occurs, alternator rectifier demand may be trimmed to meet the actual engine ability by the load control potentiometer actuated by engine governor. The nearly horizontal line Fg at the top of the curve indicates the maximum voltage line. This voltage is selected so that all normal operation will be below the voltage at which the rotating equipment will become subject to flashover. The second figure shows the family of curves representing the alternator rectifier demand from first notch to 8th notch as developed by the excitation system. The actual position of each curve is determined by an engine speed signal fed to the excitation system. When the engine is accelerated from one notch to the next higher notch, the alternator rectifier current increases smoothly until it reaches next notch value as the engine gets to the corresponding speed for that notch. Shown here is the block diagram of a basic excitation system. The exciter shunt field is fed from the locomotive battery through a network of resistors and exciter field transistor or EFT. The transistor EFT functions as a switch and it is turned on and off 800 times per second by pulses generated by the oscillator. The pulse width modulator or PWM controls the duration of on time as compared to off time during each pulse, thus regulating the average current in exciter field. PWM responds to several feedback signals as shown in the block diagram. Now the work related to excitation system done in Jamalpur workshop. In Jamalpur workshop, the work is done mainly on E-type excitation and excitation panel, which has 7 cards, which are inspected and overhauled. The cards are electronic, having subparts as diodes, transformers, small capacitors, resistors, etc. The usual life is 12 to 15 years and there are no such must-change items. Repairs are carried out in case of defective cases arrive. But items like capacitors cannot be repaired in Jamalpur workshop, hence they are replaced. In the Jamalpur workshop, following work instructions are followed on the Excitation Test Bench: pre-inspection, dismantling, inspection stage, cleaning, testing, assembly, and testing of panel with cards and ACCR. Now let us discuss the system components. First we have exciter generator. The exciter generator is a shunt wound DC machine of type AG2702AZ, exactly as used for battery charging. The generator is mounted on the traction alternator gearbox and gear driven by it is proportional to the engine speed. Second we have excitation panel. The excitation panel is stainless steel fabricated housing with component parts mounted on 7 plugs in type cards which can be removed for inspection. A potentiometer is provided on top of plate of card to adjust alternator demand. Third we have the armature current control reactor or the ACCR. The ACCR is a measuring device which when powered by an AC source produces a signal proportional to the alternator rectifier current. A reactor offers the advantage of isolating the output circuit from the main high voltage circuit. The AC output is fed to ACCR from secondary of the oscillator. The reactor consists of a large bus bar, 2 cores, 1 AC winding, 1 turn winding and 1 DC winding. One turn winding is a copper wire connected to large bus bar and forms a parallel path with the bus bar from the main rectifier current. The cores with AC and DC windings are assembled around one turn winding, calibrated and sealed in epoxy. The ACCR is connected in series with the rectifier output. A small fraction of the rectifier current flows through one turn winding which is proportional to the main current. The AC output of ACCR is proportional to the current in one turn winding, which in turn is proportional to the main current. Fourth, we have the pulse width modulator or the PWM. The PWM is a self-saturating reactor with 5 DC windings and 2 AC windings fed from one of the oscillator's secondary. The function of PWM is to control the time in which the exciter shunt field is excited by controlling the main alternator output. It has 2 cores with 1 AC winding on each core and 5 DC windings on both cores. The function of each DC control winding is as under. Exciter suicide and stabilization winding reduces exciter voltage to nearly zero when GF contactor is open, and also provides exciter stabilization when GF contactor is closed. Main excitation control winding fed from the mixer circuit turns excitation off to main proper load. Wheel slip power reduction winding reduces excitation during the operation of the wheel slip system. 2 other windings are for dynamic braking control, which are not applicable here. Next we have the oscillator. The oscillator is an AC power supply used to supply power for various control functions. It operates from a DC input voltage from the locomotive battery. The oscillator circuit is shown as such. The oscillator transformer or the OST has a number of secondary windings to supply AC power to various circuits. The power supply consists of a saturating transformer alternately energized in opposite directions. Transistors which function as switches cause flux reversal in the transformer core. The oscillator changes DC input to a 400 Hz square wave output. Next we have the mixer reference circuit. In the mixer network, the signals from ACCR and VCR are compared against each other and the reference signal. 2 outputs are connected in such a way that only whichever is larger actually supplies the current. The other one then has no effect on the external circuit. The adjustments are so made that at point F, VCR output exceeds that of ACCR and the line FG on the characteristic curve is determined by the VCR output. Now the voltage control reactor. VCR is a measuring reactor which provides a signal to mixer circuit to limit alternator rectifier voltage. This reactor also consists of 2 cores around which is wound by 1 AC winding and 2 DC windings. The operation at this reactor is similar to the operation of ACCR. More is the DC current in DC winding, more is the AC output. The AC winding is connected to one of the secondaries of the oscillator transformer. One DC winding is connected to AR output through a series of resistors to control the output voltage. It provides isolation between high voltage of rectifier to the control circuit. Next we have the exciter field circuit. The exciter field is fed from the locomotive battery through a network of resistors EFR1, EFR2, EFR3 and EFR4 and the transistor EFT. The power transistor EFT is turned on and off 800 times per second as explained before. With EFT turned on, current flows through exciter field via EFR1, EFR4 and EFT. When EFT is off, a negative current is permitted to flow through exciter field via diode XD23 and EFR4. This helps to reduce rapidly the exciter voltage. Now we have the exciter, suicide and stabilization circuit. With the throttle in idle position, the alternator field contactor GF is dropped out and exciter is connected in a suicide circuit through PWM winding connected between 36W and 61EE. The normally closed contact of GF between 61EE and 61E and ER15 resistor. This DC current in PWM winding affects the current in the AC winding in such a way that it causes the transistor EFT to switch off and cut off current in exciter field. Diodes XD18, XD19, XD20 and XD21 clamps the voltage across PWM winding to approximately 1.5 volts in both directions. Capacitors EC1 and EC2 are used to stabilize the exciter during motoring operation with EC1 capacitor disconnected above notch 3. Next we have the engine speed reference. The tacho generator on the diesel engine generates 3-phase AC with the frequency proportional to the engine speed. This is fed to a saturating type transformer whose secondary voltage is proportional to frequency. This has minimum effect of either temperature or voltage variation. The ESST output is utilized to provide smooth change of current limit, voltage limit, power limit as the engine speed is changed from one notch to other. To achieve this, three-phase output from secondary of ESST is rectified by a diode bridge ECRT3 and fed through XMLR2 via 32D of mixer circuit. Next we have engine load control. Governor load control potentiometer or LCP is connected in the circuit through LCR1 and LCR2 resistors. The potentiometer LCP is normally held at minimum during normal working of engine. In case of excess load on engine, LCP moves and a higher voltage appears at wire 29A passing current through PWM winding, reducing the excitation. Now let us discuss the second electrical component, which is the engine control panel. The engine control panel consists of control devices which regulates, rectifies and adjusts AC speed signal from the engine tacho generator. It also carries components for use in governor stabilization and speed circuits. An engine speed sensing transformer or ESST located in the left of ECP panel receives frequency signals from a three-phase AC tacho generator. This saturating transformer has three secondary windings connected to three-phase full-wave bridge rectifiers. The rectified output of each secondary functions separately as follows. It controls engine speed through engine governor. It provides a reference signal to control instantaneous values of traction generator, voltage and current. It feeds signal to the function generator module to control the intermediate notch horsepower limits. Our third and the last topic of discussion is the transition system. The purpose of the transition system is to obtain higher speed of the locomotive and still utilize the constant horsepower of the engine at the speed setting. The output characteristic of the traction generator as determined by the excitation system is such that it holds the diesel engine at approximately constant horsepower at a particular speed setting. When starting the locomotive and at lower locomotive speeds, the main generator supplies a high flow of current to the traction motors. As the traction motor armature begins turning, they generate a voltage commonly known as back EMF. This back EMF is as if increases the effective resistance to the current flow. Therefore, as the locomotive speed increases, the generator voltage must increase to maintain the traction motor current. The traction motor current will decrease, however, because of the constant power characteristic of the generator. With further increase in locomotive speed, the back EMF reaches the voltage limit of the generator and the generator current starts falling and the horsepower reduces. However, by changing the generator motor connections, the back voltage is reduced and the generator can force more current to motors to enable acceleration. To achieve higher starting torque, sometimes two traction motors are connected in series during starting of the locomotive. In these locomotives, the back EMF can be reduced by changing their connections from series to parallel. Back EMF can also be reduced by weakening the motor fields. The change in motor connections or weakening of fields is known as event of transition. The number of events are decided depending on the generator characteristic and number of motors. Now let us discuss the system of operation of the transition system. Since transition is based upon locomotive track speed, in order to control transition, an accurate indication of the speed is required. This speed-sensitive signal is generated by the axle alternator in combination with the saturating transformer. The saturating transformer requires the same amount of volt-seconds to saturate it, regardless of the speed at which saturation is achieved. The area of each pulse remains same regardless of the speed. However, when rectified and filtered, the high-speed signal will result in a higher average voltage than the low-speed signal since there are more pulses per unit time due to higher frequency. Since average voltage is related to frequency and frequency is directly related to speed, a straight line characteristic of average volts versus speed can be obtained to give an accurate measure of speed. I hope you find the video interesting and informative. Thank you.